This is Jack Jackson back again with part 6 of our series of lectures on continuous distributions. In this lecture we're going to be talking about sampling distributions, and eventually this will lead us to the central limit theorem. Probably one of the most important ideas in all of statistics. The basic idea is that we're taking an experiment and we have a distribution of individual things, of individual items that we know. For example, like say rolling a die we'll use for this lecture. We roll a die, we know what the distribution of individuals is. It's a probability of 1/6 for each of the possible dice rolls when we're rolling one die. But what if we take a sample of say size 5? We roll 5 dice. And then we compute some statistics. Maybe it's mean or median or variance or standard deviation or something like that. And we look at the distribution there. So the first thing is, do we expect the experiment to have the same results every time? Well, of course not. We know that there's going to be some natural variation there. So we might do this experiment and see what happens. For example, we could look at the means. We take 5 dice, roll them, compute a mean. There's one value. Take the dice, roll them again, compute another mean. There's another value. It's a value of x bar. Do another dice roll, another x bar, and again, and again, again, and so forth. And we get a whole bunch of these x bar values. And then we could graph those, and we get some sort of distribution. The next question is, does that distribution, what does it look like? Does it look like the distribution of the individuals, or is there going to be some difference? How are they the same? What's different about them? How does their statistics, or their parameters actually from these distributions compare? Like, how does the mean and standard deviation of the distribution of sample means compare to the underlying distribution of individuals? Like, how does that compare to the mean and standard deviation of the underlying distribution of individuals? Or say we do the same thing for the median or the standard deviation. So let's actually do an experiment like this and see what happens. So the experiment we're going to try, this is really what I've already described. We're going to roll a set of 5 dice. On each row, just to make our bookkeeping a little bit easier, we're going to arrange them in order, in increasing order, and we're going to fill them out. So for example, let's say I roll a dice and I get a 5, 3, 1, 6, and 1. Then I'm going to put them in order, smallest to largest, 1, 1, 3, 5, 6, and I'm going to enter them on this table down here and enter them in as 1, 1, 3, 5, 6. So the lowest one will be here on minimum, the maximum will be there. And notice that since there are 5 dice that I'm rolling, the one in the middle will automatically then be the median if we put it like this. So the third one will be the median. We also want to compute the mean. So the next thing I'm going to do is add them up. In this particular example, they add up to 16. And then, of course, all you have to do is divide by 5 then to get the mean. And so now we have the mean of that particular row. So what we want to do is do this experiment, and we want to do this experiment 20 times. So for example, here I've done the experiment once. I want you to do this experiment yourself 20 times and make you a new table. You can erase this first row and put your own data in there. And make a table of 20 rows. So that means that you're going to be rolling the dice, a set of 5 dice, 20 times. So there'll be actually 100 different dice being rolled eventually, or the same dice rolled many times. But you're going to have 20 sets of 5 data, 20 lines here, and figure out of course, the median and the mean there. So start by just getting this data, and we'll do that. Also, then, once this is done, we want to do a couple other things. So once we have our 20 rows of data, we want to make the following kind of table that's a frequency and relative frequency table. We want to do it for individual dice rolls here, and we have the different possibilities here for the individual dice rolls. Put the frequency that you actually observe, and then the total, and divide out and get the relative frequency over here. You can put it in a decimal or percent form. Okay, and then what we want to do is we want to graph a relative frequency histogram. Of course, those are empirical probabilities. They're not really probabilities, but they're experimental results that are approximating probabilities and see what we get there. Then do the same thing for the medians. So go back here. Now if you got, let's back up a minute. So if you have 20 times and you got times 5 dice on each row, that's 100 dice. So this frequency should total up to be 100 right here. So actually, since you're dividing by 100, all you're going to have to do is just stick a little percent sign on the end, and you make them into relative frequencies too. Okay? Now, then we also want to do the same thing for the medians. So change this word individual to median, make a similar table, and notice that they'll be taken just from this center column here in this table here. Okay? And then also we want to do one for means. Now, as you saw in the table here, the means, since you're dividing by 5, you can get a remainder of 1, 2, 3, 4, 0, and so that means your decimals here could go up by 1/5, which is 0.2, go up by 0.2. So you're going to have, well, you're going to have 1, 1.2, 1.4, 1.6, 1.82, and so forth. So there are actually more choices for the mean. So the table is going to be a bit bigger, but the same idea, and record those. So let's review what we're going to be doing. We're going to roll 5 dice, put them in order, write the information here, go ahead and compute the sum and the mean. And the median will automatically be computed by putting them in order. Do this 20 times. When you're done, look at all the individual data values. Count how many ones you've got on the whole list of data. And put that as the frequency here. How many 2s do you have altogether of the individuals here? 3, 4, 5, and 6. Those should total up to 100. Then divide by 100 and get your relative frequency here in either percent or decimal form. Now, then one more thing. Then take these and make a histogram, make a bar graph with these here. Next, go through the medians. Now, this time you're only going to have 20 numbers here, but take these 20 numbers here, count how many 1s, how many 2s, 3s, 4s, 5s, and 6s, add those up, it should total up to 20, and then divide by 20 there and get your relative frequencies, and again, make a bar graph. Finally, go back and look at the means here. And of course, there are a lot more possibilities for the means. They'll start at 1 and go up to 6, but they'll go up by, not by 1s here, but they'll go up by 0.2 each time. That's 1/5, 20%, 0.2. And then find how many 1s, how many 1.2s, how many 1.4s, how many 5.6s, and so forth. And put all those numbers in there. They should again total up to 20 because you're doing, again, these 20 numbers that you're going to have in this last column. And then divide by 20 to get your relative frequency there, and again make a bar graph. And before you begin, I want you to try to make a prediction. What do you expect to see in the shape of the bars and the heights of the bars? Of course, they're all rectangles, but the overall shape of the distribution in the histogram. I think you know what to expect for the individuals. Question is, do you expect the same thing, the same shape of graph for the medians or the means, or do you expect something a little bit different? What do you expect to change? Make your prediction up front, then do the experiment and see what you come up with. Okay? So this is going to take a little bit of time. Go ahead and stop this video, do that, come back. Press pause now. Okay, now that you're back, you should have actually done this experiment. You should have a table like this that you've put together. Maybe you even did that in Excel, for example, and collected your data, or maybe you wrote it down by hand, and then you computed these relative frequencies, and then made histogram out of it. Now, I've done this experiment with students in the classroom, and we've done this many, many times. We've got a total of 700 experiments, different students doing them. So altogether they did 700 rolls of 5, which is actually 3,500 individual dice rolls. And here's the data that they came up with, and the number of 1s, 2s, 3s, 4s, 5s, and 6s. So this is actual data from a fairly large sample size. And of course here, well, I've got the table backwards from the way I had it there. Here's frequency, here's relative frequency. But there's relative frequency. And what what do we see there? Well, we see about what we would expect to see. The law of large numbers tells us that eventually this is going to approach the theoretical distribution. And of course, what is that theoretical distribution? Well, we know that it is the probability of each one is 1/6. That's actually 16.6 repeating percent, about 17% each. And we see that those bars are all exactly the same height. Now, when you go back here, we see they're not exactly the same height, but they're very, very close. With this large of a sample size, we would expect these bars to be quite close, and these probabilities to be very close to being all the same. And sure enough, that's what we get. They're all very close to the same height, and the probabilities are close to being the same. Now here's the question though. What about the medians when we compute those medians? Well, here's what the data came out to be. Of the 700 rolls that we did, 700 groups of 5 dice being rolled, notice that you're a lot less likely to get a 1 or a 6. Now let's think about it. What would it take to get a median of a 1? Okay, a median of 1 would say that the third from the smallest, from the smaller end, the third one would have to be a 1, which meant you had to get at least 3 1s. Well, the probability of getting 3 1s, at least, is relatively small. It's a lot more likely to only get 2 or less 1s, which would be a higher number for the median. Similarly, to get a 6, you'd have to have a median of 6, you'd have to have at least 3 6s. Again, that's going to be a little more rare. But it's very, very common to get these numbers in the middle, a 3 or 4, because there's lots of different ways you could get that. And so here's the experimental data of what came out. What about the actual theoretical? Well, theoretically, here's what we should see. We should see roughly 4% for the 1 and the 6, about 17% for 2 and 5, 29% for 3 and 4. So notice actually the 2 and 5 came out to be about the same as they did for individuals, but the 6 and 1 were decreased and the 3 and the 4 were increased. So we see it kind of higher in the middle, lower on the ends. It is symmetric in this case, and we see it leveling off there on the coming off towards 0 on the ends, getting smaller probability. Now what about means? Well, again, with means, there are a lot more possibilities, and so they go actually from 1 to 6, going out by 0.2s. And here's the data on the first 700 times we did this. I actually did that in class this semester, and somebody actually rolled 5 1s, which is the only way you could actually get a mean of 1. It's possible, but it's a very low probability of that happening. That data is not included in this set. This only goes up to the first 700 times we did this. But you can see what's happening here is what we have. Now, I kind of painstakingly figured out the actual probabilities here. I'll show you the spreadsheet where I did this. It took a little time and effort to do it. It's something you could certainly do, but it would take a little time to do it. But anyway, I've worked out the actual probabilities, and here's what they are. So the probability that you'd actually throw all 5 1s with one roll is less than 0.01%. In other words, 0.0001 in decimal form. It's about that. Same way for throwing all 6s. And so we see the probabilities, and again we see it smaller on the ends and higher in the middle. And look at what's happening right there. The bars at 3.4 and 3.6, those are the highest ones. They're a little over 10% each, and then it levels off at the ends. Look at the shape of that graph. Does that look interesting to you? Does that look like something we maybe have studied? Do you kind of see a bell shape to it? Something kind of like a normal distribution? That's not a coincidence. That happens all the time, that this thing starts getting closer to a bell-shaped curve. And that's really the crux of the central limit theorem that we're going to talk about a little bit later. Now, let's continue this idea. We're going to perform an experiment from taking a sample size n from a known population. We're going to compute a statistic such as we just did with the median and the mean. We can do the same thing for the standard deviation or variance or any other statistic. And if we repeat the experiment, there will be some natural variation in the values of the statistic from each sample. Of course, the graph that you got didn't necessarily look like the graph of the ones that I had here with the sample of 700 rolls. You had a sample of you only did 20 rolls, and somebody else does another one of 20 rolls. They're going to look a little bit different, so there's some natural variation. But if we do it a lot, we should get something pretty close to the theoretical setup. Now, if we form a distribution where the random variable is the values of these sample statistics, like say the sample means, then these statistics, the sample statistics, have a distribution of their own. And the shape of this distribution is different than the shape of the distribution of individuals. Were you surprised when you found that the medians and the means weren't just straight level, the same height bars as they were for the individuals? If you think about it a little bit, you realize that it's really difficult to get those values on the ends, and more likely to get the ones in the middle. So maybe it's not too surprising once you think about it. Maybe you predicted that, maybe you didn't. But now that you see it, I think you can understand that it's reasonable that you're likely going to get more in the middle than on the ends, really for both the median and the mean. But the point is they have a distribution, and this distribution has a different shape. And in the case of both medians and means, it's more mound-shaped. In other words, kind of humped up in the middle, extended up in the middle, and then kind of trailing off down towards zero on the edges. Now, these distributions have parameters. Remember, a population has parameters, sample has statistics. So here's a distribution of our individuals, and we can compute the mean and variance of this distribution. And let's review how we do that. First of all, we need to know the values of the random variable x and the probability of each. Well, the values of the random variable x are what you can get on rolling an individual die. This is for the individual die, an individual die. So x could either be 1, 2, 3, 4, 5, or 6 dots on the top. And they all have equal probability of happening if we assume this is a fair die. And so each of those has probability 1/6. That's 16.6 repeating percent, or about 17%. Of course, if you add up all those probabilities, you get 1. Now, to find the mean, remember it's the expected value of x. That is, you take x times the probability of x for each x value and then add those up. And so we take 1 times 1/6, 2 times 1/6, 3 times 1/6, and so forth. And we get these numbers in this column right here that says x times the probability of x. We add those up, it turns out to be 3.5, right in the middle. And of course, in this case, since they're equally weighted, we could have just averaged 1, 2, 3, 4, 5, 6, and it would have done the same thing, and we got 3.5. In general, when these probabilities are different, this multiplying the x by the probability and adding them up gives you a weighted average, which gives you the correct mean. Now, there's a couple of different ways we can do the variance. It's the expected value of parentheses x minus mu, close parentheses, squared. But it's also the expected value of x squared minus the mean squared. And so I'm going to use that second alternative formula to compute this time. So I take all my x values and square them. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and so forth to get this next to the last column on the right. And then I take each of those times the probability. So 1/6 times 1 is 0.16 repeating. 1/6 times 4 is 0.6 repeating. 1/6 times 9 is 1.5, and so forth to get these numbers in the last column. If we add those up, it turns out to be 15.16 with the 6 repeating, and that is the expected value of x squared. So we take this 15.16666666 and subtract from that the 3.5 squared. And you can check that out on your calculator or spreadsheet, and you'll see that that gives us the variance of 2.9167, actually probably 6 repeating there actually. And so there's the mean and variance. Now that's just of individual dice rolls. rolling one single die over and over again. So now the question is, how do the parameters of the one that we just worked out, how do they compare? Well, actually rolling 5 dice is a little bit more complicated. So let's go back and we're going to do an easier experiment first. Okay? So we're going to actually do this with only 2 dice. And with 2 dice, it's pretty easy. We've actually already pretty much done this already. You should be able to work out what the table is for the distribution of the means. Hint, it's just the sum divided by 2, and we already have worked out in an earlier video, we worked out the distribution of the dice when we were rolling 2 of them. So the question is, how does the mean and the variance of the distribution of sample means compare to the mean and variance of the distribution of the individuals? So we're not going to actually do this experimentally, we're going to do it theoretically. But the idea is to roll 2 dice, find their mean, record that. Roll 2 dice, find their mean, record that. And see what that distribution of means would be. So let's work out what the table would be for the PDF and the graph the PDF of X bar, the distribution of X bars, and then compute the mean and variance of this distribution. And you want to compare these values then to the corresponding parameters of the distribution of individuals. In other words, we want to see how the mean of the means compares to the mean of the individuals. How the variance of the means compares to the variance of the individuals. So see if you can go ahead and work this out. Press pause now. Okay, so what we've done, if you remember, we've done this problem before, and if you need to see this, go look back at an earlier video where we were doing compound probabilities with rolling 2 dice, and we saw that the sum could either be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12, but there are actually 36 different possibilities. One of those had a sum of a 2, 2 of them had sum of 3, 3 were 4s, and so forth. And so we got probabilities of 1 over 36 for 2, 2 over 36 or 1/18 for 3, 3 over 36 or 1/12 for 4, and so forth. Now when you're finding the mean, we're just taking the sum and dividing by n. N is 2 here, so it's just the sum divided by 2. So the means are 1, 1.5, 2, 2.5, 3, 3.5, and so forth up to 6. And so we see the values of X bar are given in the second column on that table on the right, and the probabilities, both in fraction and decimal form, then are given in the last 2 columns. If we graph those, the frequency histogram, actually the relative frequency histogram, well, actually it's a probability distribution PDF this case because it's not experimental data, it's an actual distribution. So if we graph the PDF, we get this bar graph on the left, and what we're graphing, the heights are the probabilities, and then the X values at the bottom are really X bar values, the mean of a pair of dice. Now remember that individuals turn out to be, where is it back here? There's the theoretical probability for the individuals. They are all bars the same height, and they have probability 1/6. Here's the mean of the individuals is 3.5, and the variance is 2.9 something. So here's the table for the mean of a pair of dice, a sample size of 2, and so we're doing sample means from a sample size of 2. Here's the table for the values of the mean and their probabilities, the table for the PDF of this distribution of sample means. That's on the right, and then on the left you have the graph of that PDF. Now let's find the mean and variance of this particular distribution. So we can use the stuff that's in this table, perhaps maybe with a spreadsheet or by hand, and figure out the mean and the variance. So if you haven't done this already, go ahead and see if you can use this example that we did back here for finding this technique for finding the mean and variance of the distribution of individuals, do this for the sample means. Do that with this table here. And remember, our x's are actually the means. You can just basically ignore this first column. Okay, go ahead and do that now. Press pause. Well, what you should have come up with is a table that looks something like this. Now, I definitely used Excel to help me out with this. And so you see the means and their probabilities. If we multiply the mean by the probability, we get 1 times 1/36 is 1/36, or about 0.0278. 1.5 times the probability of a 1.5, which is 1/18, 2/36, and we get this 0.0833. We have the mean of 2, and the probability of that is 3/36, or 1/12. Multiply those together, we get 0.1667, roughly. And so we add all those together, and we get the mean, which is 3.5. We can also get the variance if we use this alternative formula for the variance. We want to square the means. The means are the x bars. So this first column on the left could be labeled as the mean, or it could be labeled as x bar. And so we want to take the x bars and square them. So 1 squared is 1, 1.5 squared is 2.25, and so forth. And then we take all those x bars and multiply them by the probabilities. So we take the 1/36 times 1 to get 0.0278. We take the 1/18 times 2.25 to get the 0.1250, and so forth, to get all these numbers in the right column. Add those up, we get 13.7083. That's the expected value of x bar squared. To find the variance, then, we take that number, the expected value of x bar squared, minus the mean of the x bars squared. So in other words, we take this 13.7083 minus the 3.5 squared, and we get 1.4583. Okay, now let's back up just a minute. When we look at the distribution of the individuals, look what the mean was. It was 3.5, and that's our measure of the center of that distribution, 3.5. Look what the mean was for the x bars, also 3.5. So look what happens is when we're doing the distribution of the average, the means of our the mean of our means, okay, we're finding the average of our x bars, the mean of the means. It turns out to be the same as the mean of the individuals. So the average of the averages is the same as the average of the individuals, which means that it didn't change our center whenever we looked at this this method of doing the distribution of the samples. So this also helps to tell us that x bar is a good estimate of the mu for the population as well, because it's not shifting around on us. It's centered up the same way. But look at what happens with the variance. Something's interesting here. Let's go back to here. Here the variance was 0.29167. And over here that was for the individuals. And for this one we get a variance of only 1.45833. So for reference, here's the variance of x down here, 2.91667. And the variance of the x bars is 1.45833. So the first thing to notice is that the sample has less variability. We can tell that by looking at the picture as well, right? The pictures were just bars going straight across for the individuals, but you can see it's more humped up toward the middle, less spread out from the middle when we're rolling 2 dice and finding the mean. So there's less variability in the means. How much less? Well, look what happens here. If I take this variance of x and divide it by 2, I get exactly the variance of the x bars. And that 2 was how many dice we were rolling. That's an interesting thing. So we have an interesting relationship that the mean of the x bars is the same as the mean of the x's, but the variance of the x bars is the variance of the x's divided by the sample size. Let's do the same thing with the distribution of 3 dice rolls. This one's a little bit more tedious to work out. Before I finish this video, I'll show you my spreadsheet where I've worked this out, and it's available to you. in this section online as well. And I did this in Excel. It took a little bit of while to do it. But here are the different possibilities for the mean. 1, 1.3 repeating 1 1/3, then 1 2/3, 1.6 repeating, then 2, 2.3 repeating, 2.6 repeating, 3, so forth. And the probabilities are worked out there and graphed. And if you look, what do you see? You see something that looks even more like a normal distribution than we had before, and we're going to see even less variability. So if I go ahead and work out the statistics for this one, once again, I still get a mean of 3.5. So again, we're not shifting the center. And then we get a variance, though, that's even smaller still than what we had before. In fact, if you take the variance of the x's and divide by the sample size, divide by 3, we once again get the variance of the sampling distributions. In other words, the variance of the x bars is the variance of the x's divided by n. Very interesting result there. A lot of computations here. It starts getting very useful to have a spreadsheet to help us with this. And of course, we already did the one with 5 distribution where we're throwing 5 dice, and this looks even more and more like a normal. This one looks very much like a normal distribution here. And again, I'll show you a little bit later on how I got these theoretical probabilities. But here's the details, working out the variance and the mean. And once again, the mean is 3.5, and the variance here is the same as the variance of the x's divided by 5, divided by the sample size. And so we see the larger we get the sample size, the smaller the variance is going to be. The more consistently it's going to be grouped around the mean. And the more the sample, the distribution of the sample means looks more and more and more like a normal. So here's the one of the bottom lines that we found out here. The mean of the sample means is the same as the mean of the distribution of individual items. We could do that, say that symbolically as mu of the x bars is the same as the mu of the x's. But samples are less variable. They have the same center as individuals do, but they have less variability. Specifically, the variance of the sample means is the variance of the individuals divided by the size of the sample. So the sigma square of the x bars is the sigma square of the x's divided by n. Of course, then if we want to find the standard deviation, we just take the square root of both sides, and we see that the standard deviation of the x bars is the standard deviation of the x's divided by the square root of n. And so this tells you how the mean and standard deviation are going to compare. No change in center, the same mean for x bars and x's, but there is a smaller variance, smaller standard deviation. The standard deviation of the x bars is the standard deviation of the x's divided by square root of n, or perhaps even simpler formulas on the variance. The variance of the x bars is the variance of the x's divided by n. Now the central limit theorem is basically says what we've just discovered, is that it's not just about rolling dice, but in general, for any distribution we have, the distribution of sample means from any underlying distribution of individual items approaches a normal distribution as the sample size gets larger. So the larger and larger the sample size we have, the closer and closer that distribution of sample means is to a normal distribution. The mean of this distribution of sample means is the same as the mean of individuals, what we just noticed. And the variance of the sample means is the variance of the individuals divided by the size of the sample n. If the distribution of individuals is exactly normal, the individuals are normal, then the distribution of sample means is exactly normal regardless of sample size. Of course, it's normal with a sample size of 1 because that is the individuals. If you do 2, it's a normal with the same mean but a smaller variance, the old variance divided by 2. variance of individuals divided by 2 will be the variance of the distribution of x bars for a sample size of 2. And if we have a sample size of n in general, and we start with a perfectly normal with mean mu and standard deviation sigma, then no matter what n is, the distribution of x bars, the distribution of sample means, will be exactly normal with the same mean, so it'll still be mu, but the new standard deviation will be the old standard deviation of individuals, sigma, but divide by the square root of n. And again, that doesn't matter what the sample size is. However, we'll see that if the distribution is highly non-normal, particularly if it's bimodal, not symmetric, this kind of thing, then the sample size might need to be pretty big. And usually our rule of thumb is if the sample size is over 30, then usually almost any distribution you can come up with will be approximated pretty well by a normal distribution. If we know what the mean and standard deviation of the original distribution was, then we know the mean and standard deviation of that normal distribution. And of course, we know lots of things about a normal distribution. We have lots of cool shortcuts on our calculator for them and so forth. This is the key to doing inferential statistics, is understanding this particular thing. So a lot of times we have to get the sample size to be pretty big before we know that this works. And so it says if we don't know anything about the underlying distribution, as long as we've got a large enough sample size, we can still assume that that distribution of sample means is normal, or at least really close to it. And a size of 30 will do that for us. Now, if we don't have it up to size 30, sometimes that's still plenty. As we saw before, if it's exactly normal to begin with, and it doesn't matter what the sample size is, the distribution of sample means will also be normal. Now, if we have some distribution that's kind of mound-shaped, kind of symmetric, not really skewed a lot, it's kind of mounded up in the middle, trailing off on the sides, probably a real small distribution will work. We saw that a sample size of 5 gave us something that was pretty close to normal, even when we started with a uniform distribution. Now, there are a couple of applets online that illustrate some of this concept of the central limit theorem, and here's one that I pulled some screenshots from. This does a simulation to approximate some of these distributions. So if you look at the screenshot, you can see the web address there on the left, and then you'll get to this screenshot on the right. And notice in this one I have done a whole bunch of samples. I moved this bar for a number of samples all the way to the right. And I've started, though, with a pretty small sample size, only 2. And I started with something that's uniform, and we see what the graph looks like there when we did a sample of, and this particular one has, we were given the mean and standard deviation here, and a sample size. This is individuals, a distribution where they actually did 16,000 things and sampled them and did a histogram. Now, these bars are not exactly even. They would be if this was a truly the theoretical, but this is from an experiment. Okay, and you see roughly bars about the same height. Then what do you see? You see roughly a triangular kind of distribution here whenever we do samples of size 2. Here we go. The one on the left is taking the same distribution, okay, but we did samples of size, we pulled samples of size 8 from this population of 16,000 here, which was approximately uniform. And look at this, we're already seeing something that looks very much like a normal shaped curve. And this whole thing is less variable than the original individuals up here. Now, if we go a bit farther, and this time I did a sample of size 30, you can see very much looking like a normal distribution, also a very tighter, smaller standard deviation here when sample size is 30 than the original one has. Then the one with sample size 8 over here are certainly more than the original distribution. a smaller standard deviation, smaller variance. Okay, what if you get something that's kind of skewed? So here we have a skewed distribution. It's a lot higher on the right, on the left, and it's skewed to the right because that tail is going out to the right. And this one has 16,000 here, and we do samples of size 2. They did 4,000 samples of size 2, and we get this distribution here. It's still skewed a bit. You can definitely see the skewing going on, but it's already starting to look more like a normal. By the time we get to sample size 8, here I just pulled off this bottom screen and showed it to you here. Now we're already looking pretty much like a normal distribution, and normal would be a pretty good approximation. And notice this has less variability than the ones that's sample size 2, and certainly less variability than the original population. And then if we go to sample size 30, definitely a normal distribution is a very good model for this one, and has an even smaller standard deviation. The one that's probably that really takes us to get up to 30 before we really see normal is if it's highly if it's bimodal. That's really the worst one, and the modes are kind of spread out here, and I even made it where it's not symmetric. So you can see that population there again of 16,000 individuals, and you can see the distribution there, humped up on both ends but not in the middle, right? It's down in the middle. Very non-normal. That's almost as far from normal as you can probably get. Okay, and then if we look at that, then we do samples of size 2. It's not really looking like normal yet, but we're also seeing kind of the humping up going on in the ends and three humps here. And we go to sample size 8, where overall the kind of thing is starting to look kind of like normal, but we definitely have these ups and downs in between. By the time we get to sample size of 30, though, we definitely start to see something that looks very much like a normal distribution. Now there are a couple other places here where we can look at some of these different applets, and let's take a look at some of these. Let's see if this will take us to place here. Yeah, this one will go here. This one is someone's put this together, and let's take a look at something here. So I'm going to do this with a large population size, and we can draw with size 1, sample size 1, this is the individuals. So again, this is using some sort of sampling technique. This is going to be an approximation, a numerical approximation. So we have a population 361,145, and so we should see something that's basically just straight across, bars all the same, a uniform distribution going straight across. And so we get an approximation of that. But if we increase the size to 2 and then narrow draw it, now look what happens. This is the distribution of means. And notice what you see, it went from straight across bar to a triangular distribution. Let's increase it to 3. Even with the sample size of 3, we're starting to see something that looks very much like a normal distribution. Let's go to sample size of 4. This is going to look even more like a normal distribution, and it's going to be less variable. Increase to 5. This is kind of like the dice roll experiment where we had a normal, uniform distribution, and then we did samples of size 5. We got something that's very close to that. Let me increase this a bit more. Let's go up to 10. Now, again, this is experimental data, so it's not going to be perfect. But if we did this as a theoretically, the curve would look very much like a normal distribution at this point. So let's go on to our sort of rule of thumb of 30, and we're going to see it. They're changing the scale on this. It's actually getting taller and skinnier, and so the standard deviation is going down. You could actually look at those standard deviation numbers. Now let's go back to a different distribution. What if you have, let's say, a triangular distribution where the mode is all the way to the right here, and so the graph of the PDF is actually just a straight line, not horizontal line this time, but an increasing line, positive slope line. What if we take this and do samples of size 2? What are we going to get? Well, that one was highly skewed to the left, and And the distribution of means is still skewed to the left here. We can definitely see the skewness going on here with sample size of 2, but it's already starting to round out and look more like a normal distribution. Sample size of 3, the skewness is still there, but going down, looking more like a normal. Here's a sample of 4. Now it's starting to look more like a normal. Okay, and we're still seeing a bit of skewing here. But by the time we get up to, say, size 10, this one's pretty darn close to a normal. If we go up to 20 for our sample size, what do we see? Something that's very close to normal there. And certainly by the time we get up to like 30, that's definitely going to have that normal looking shape for us. Again, this one's done from some sample data. Okay, here is it's basically like it's uniform in sort of 3 pieces. It's like a step kind of thing. So you got a horizontal line here, a lower one in the middle, and a medium-sized one on the right. This picture here kind of shows you what the distribution is supposed to look like. This is our distribution of individuals when we do a sample from that distribution. And here's what the means would look like when you're doing a sample of size 2. Again, we see some not normal yet. We definitely see this trimodal kind of look here, or 3-peak look anyway. Here are 3 for my sample size, starting to level out, but I still see the definite difference in the peaks. Here's 4 for a sample size. Notice it's starting to level out, getting a little bit closer to being symmetric. Those ups and downs are starting to kind of smooth out a little bit, and the whole thing is starting to approximate a normal distribution. Let me go on up to 8. Alright, now by now, boy, that's starting to really look like normal. And there's it for 10. And see, by 10 we're already up pretty close to normal, even though we started very non-normal. And certainly by the time we get up to 30, very much looking like a normal distribution here again. Also, again, as that sample size got bigger, our variability got smaller and smaller. What if we start with just a distribution that's kind of a V-shape distribution? That's the distribution of individuals. Look what happens with the means. So we got a couple of about 3 different peaks here. But even with sample size 2, we did get that biggest peak in the middle. Here's with 3. Here's a sample size 4. We're going to see that peak in the middle here. 5. 5, we see the twin peaks toward the middle. Let's flip ahead to maybe 10. Okay, and so this one here, oh, look at that. With the sample size of 10, we're already pretty close to normal. Close enough we could use a normal to approximate that quite well. And certainly if we go up to 30, then definitely we're going to see a normal looking shape. What if it starts normal? Well, if it starts normal, then it's normal to begin with, and every one of these is going to be normal. Okay, so our sample data is approximately normal there. And then this one's going to be normal as well, but look at what happened to the standard deviation. That standard deviation gets smaller and smaller. If we were to graph these on the same scale, they would get taller and skinnier as we continue up, increasing our sample size. Here's what a bimodal situation. Okay, what happens if we do a sample of size 2? There we go. Again, getting closer and closer to normal as we increase that sample size. 3, we're sort of getting kind of close to something that could be maybe approximated by normal. Oh, 4. That's better. That's looking more like normal. How about 5? 5 is looking very much like normal. Let's skip ahead. 10. Ah, very normal looking. 20. It's getting less and less variable. Right now the standard deviation is 5.1. Let's go to 30 and see what happens. Standard deviation now is 4.2, so it's getting less and less variable. Here's another one of individuals that is definitely skewed there. And with the sample size of 2, we can still see the skewing going on, but it's not as pronounced. Still can see a little skewness there, but almost normal. And looks like by the time we get to be 4, or especially 5, and now we're talking about something that's pretty much like a normal. This one might be an exponential function, might look like this, remember? And let's see what happens when we take something like that. That's very skewed. In fact, it was highest on the left end, but now it looks more, kind of goes up and down. Still definitely skewed there because we were highly skewed to begin with. Still see the skewness at 3 and at 4, but it is starting to become more and more closer to being symmetric. So that definitely, I think on this one, by the time we get to, say, 10, it should be pretty close to normal. And of course, if we go up even further, let's say to 30, then that's even going to be even closer still to a normal distribution. And let's see what this one here does. Okay, this is from Wolfram. Wolfram has a lot of interesting things. So here's what the normal is that it's going to eventually approach, and this is a uniform distribution, sample of 1, which is just the individuals. Okay, and I should be able to take this slider, maybe. It's not letting me grab that very easily. Let's see. Had this working earlier. Something's not working right for me here. But you can experiment with this, and there's some other different things that you can do there. Okay, so I think that gives you an idea of the central limit theorem. Let's go back and review the basics. Okay, so when we look at sampling distribution, what we're talking about is the distribution of sample statistics. We've mostly been looking at the sample means because that's probably the most important one, but we could look at sample medians, we did that a little bit, and we could even look at sample variances or sample standard deviations or any other statistics, sample minimums or maxima. Okay, but if we're doing sample means in particular, we can start with any underlying distribution, and the more we let that sample size increase, the more the distribution of sample means approaches a normal distribution. And the mean of this distribution of sample means is the same as the mean of the distribution of individual values. The variance of the sample means is smaller than the variance of the individuals. It's less variable, more consistent. And that value is found by the variance of the x bars is the variance of the x's, the variance of the individuals, divided by the sample size n. And of course that means that the standard deviation of the x bars is the standard deviation of the x's divided by the square root of n. If the distribution of individuals is exactly normal, then the distribution of sample means is exactly normal regardless of sample size, of course with the same mean and a smaller standard deviation. If the distribution of individuals is highly non-normal, then it may take a larger sample size, but our rule of thumb is, if we don't know anything about the distribution, we'll say that if the sample size is at least 30, then we can still assume that our distribution of sample means is approximated very well by a normal distribution. If we know something about the the situation with the distribution. We have some reason to believe that that distribution is somewhat close to normal. What characteristics are important? Mainly that it doesn't have the bimodal thing with two peaks, and also that it's got something kind of humped up around the middle a little bit. If it's got those things, then for sure we can get by with less than 30 for being close enough to normal that we can approximate with that. So there's an overview of sampling distributions and the central limit theorem.